No.
I said, ouchie. It makes me scared. Yeah, so let's say this takes 10, 15 minutes. The other side of this, like I said, you have a choice. You can either keep doing it the old way or you can do it the new way. The one thing you can't escape, and I brought this up yesterday, is that you have to commit starting yesterday, since we have variables on both sides now, you have to commit to an idea. And that idea, this is not something you're allowed to pick and choose. You have to take this one. You remember yesterday it came up at some point that if the problem that we're working with has a greater than, and it could be a greater than or equal to also. The equal to, if you haven't figured this out, it's relatively inconsequential, right? It's like not a big deal. But if it's a greater than symbol of any form, do you guys remember what the word is that we have to embrace? Yes, I mean, the importance of this cannot be overstated. So it's an or situation if it's a greater than problem. And on the other side of things, if you have a less than, and again, it could be less than or equal to, no matter what's the word we embrace. And these are what will get you through this. Not this whole quiz isn't this. I mean, there'll be some easier stuff like we've been doing with just numbers. And you're welcome to continue to do those the way you have been if you're finding success with that. It's just these ones with the weirdness of like you saw yesterday in the notes, how we had that one problem where there were like two shadings that went the same way and stuff like that. I just think that, I don't know, this might be a good solution. This might also be something that you wash from your memory. So problem one on your homework says the absolute value of 2x minus 7 is greater than x minus 2. I don't know why. I sure did, didn't I? So I think I'm back playing Rocket League again. So, so where this stems from is the idea of what is a basic splitter and what is a basic squisher. There's like a decent chance you get really lost in the first minute of this lecture. So make sure you either raise your hand or just cut me off and say, I'd like you to explain that again. If we go back to just the basic idea of what is a splitter and what is a squisher, because this one is a greater than, this is going to be a splitter. That's what or implies. The word or implies that we're splitting in two directions. We're going to go one way or the other, right? So I'm going to just go off to the side. I'll change colors here. You're welcome to write this part down or not. It might help you to understand why I'm about to do what I'm about to do. But I don't know. I hope you agree with this. If I gave you the absolute value of x and I told you that it was greater than 4, if you could go all the way back in a time machine to like 2 weeks ago or a week and a half ago when we first started talking about inequalities, whenever that was, we had an example. It might have been this exact example in our notes. And what we discovered about this is that if you were to graph it, does anyone by chance remember what the graph of this? I can't imagine that you would. That would be awesome if you did. But anyone remember what the graph of this one winds up looking like? Or maybe more to the point, does anyone remember where the numbers are that solve this inequality? -4 and 4 have a lot to do with this. So let's set those up as our boundaries. I don't know why I wrote 5. Negative, yeah, it's just going to be one of those. Maybe I should have stayed home today. Um, I don't know. So those are our boundary points. So the question becomes, are the numbers that satisfy this situation between the 4s or outside the 4s? Correct. They're outside the 4s. And so what we see is that to have an absolute value that's greater than 4, you either have to be less than -4, like -5 or -6, right? Or you have to be bigger than a +4, like +5 or +6. All those numbers that are in those arrows on the outside are numbers that have absolute values greater than 4. So if we were to write this out as a splitter, we could say that x is either less than -4 or x is greater than +4. Give that a second, let that sink in. We can't move on though until you agree with that, because what I'm about to do is completely founded on that. Everybody okay? So I'm going to take that idea, what I have written in yellow over there, and I'm going to use it to help me translate the problem in white and red over here. So Think about this situation. I'm going to circle it in green. That situation says that the stuff inside the absolute value can be less than the opposite of what I see. In other words, I can say that 2x minus 7 could be less than negative x plus 2. The thing that I have circled in green and the thing that I have written in green are the similar situations here. By writing a splitter, I'm forcing myself to say I could be to the left of the smaller boundary. That's what the green thing says. Okay. What this other one says, I'll circle it in red, is that on the other side, I can also be bigger than the positive boundary. Um, like the normal, like don't change x minus 2. So this one would be 2x minus 7 is greater than regular x minus 2. And of course, in between them, I am mandated to put the word or. I don't think you should give up on this method if you're already lost. There's a really good chance that you are already lost, just because that's a real big leap there. But that's what a splitter enables us to say, is I'm either going to be less than the small boundary or I'm going to be bigger than the big boundary. And I think the reason I like this method personally better is that the weirdness at the end for me isn't there. Like I just solved both of these like a robot. It's the construction of them that's always the killer with this method. Less than the little, bigger than the big. Okay. So the split is done, and now we just have to solve. Help me solve the green problem, if you would. Forget the red, just solve the green. What do we get on the left? 3x. If I add the x across on the right, I have to add 7, so I get 9. And then I divide by 3, and I get x is less than 3. Now, of critical importance here is that I write down the word or. I don't have to keep writing it like if this took me a couple, 3 steps to solve, I don't have to keep copying. But when I get to the ending statement, I absolutely have to recopy the word or like in the next problem, the word and. It's critical. So now help me solve the red one. This one I don't need to do any work on because when I bring my x across, I just get 1x just like I want, and then add 7 to the other side. And what do I get? I do. So anytime you have an or situation like this, you're never going to have no solution. I mean, I can't imagine that that could ever happen. Because remember that what or brings up is the possibility that you can be in one place or the other place. So let's take a look at what this situation looks like on a graph. If I take the green and the red and I graph them on the same number line, then what I'm going to say, and I feel like sometimes the visual aspect is what makes it click home for some people. Here's 3 and here's 5. To be less than 3 means I circle 3, leave it hollow, and I shade to the left, like this. And then I circle 5, leave it hollow, and I shade to the right. Here's a little foreshadowing for you for the next problem. Had the word or said and, what would we say? Again, I don't like to do this because it's weird, but like I would open up my wallet to you and give you every dollar in it. And I happen to have quite a few in there right now. If you could find me one number that's in both of those arrows at the same time, can you? You cannot. There are no numbers in the known universe that are simultaneously less than 3 and greater than 5. It is impossible, right? So if this said and, then we'd have a different approach. Our answer in this case, if it were and, would be no solution. But because it's an or, we're done. There's nothing else to say about this. We don't have to test points. That's the thing I think I like about this is that I don't have to go back and create regions and test numbers. Everything is taken care of for me. So as far as the solution to problem 1 is concerned, the answer to this problem is in the red box. The graph is in the red oval, and we're done with problem 1. Okay. No, never do we have to test points if we go this way. Let's take a look at problem 2. It's the leap, it's the beginning that's the hard part. And I know that none of you asked, but the construction of what's in this purple box is the hard part. Everything after that is basic algebra, moving stuff around and dividing and stuff. It's that leap when you actually write it as a split like that. Ooh, that's nasty. All right, let's take a look. Problem 2. And then I will get out of the way and I'll be available throughout the hour and just answer whatever questions. And if you want to go over a problem with me, we can go over it and you can choose like which method do you want to use, the old method that we've been doing or the new method that I'm trying to teach you today. I can go either way. You should commit to one though. I think you probably don't want to waffle back and forth. So problem number 2 says that we have the absolute value of x plus 2 is less than or equal to, which again, really mostly doesn't matter, negative 1/2 of x minus 6. So to try to get this to make sense, again, I'm going to go off to the side and write a similar situation. If I said to you that the absolute value of some number x is less than, and I can put or equal to, again, it just doesn't matter, 4. Let's go back to 4, just because we used 4 last time. Does anyone remember like what this implies? Do you guys remember from a week ago or so what numbers would make that purple problem true? Let's make a number line. Maybe it'll come flooding back to you. The boundaries are, of course, the same boundaries as the last problem, negative 4 and 4. Where are the numbers whose absolute values are less than 4? Couldn't hear you. What? In between. Exactly. Remember, to have an absolute value less than 4 means your distance from 0 is less than 4. It's like 0 is pulling you in like a magnet. And so the numbers whose absolute values are less than or equal to 4 are the numbers that are either at the boundaries or in between the boundaries, like this. And the key is you have to remember from earlier that the word, the less than sign, which word is implied when we have a less than? What's the word? And. So this is going to be an and situation. And you'll know after this next example, this one, if this method makes sense to you or not. You'll know. So what I'm going to do is I'm going to write the two situations and I'm going to put the word and in between them. I'm not going to write it like a squisher. I'm going to write it like I did the last one, only this time I'm going to be smart about how I say it. So staying with the purple problem over here on the right, if I just looked at, say, this circle and the shading going this way, I hope you would agree that what I'm saying there is that x is greater than or equal to negative 4. You buy that? But on the other side of it, I've also got this circle with shading colliding and coming back towards the other one. These are two shadings that are essentially coming towards each other. Well, how would I write the green one? X is less than or equal to positive 4. And the key here, again, is the word and. Are there numbers that are greater than negative 4 while also being less than 4? Hell yeah. It's like infinitely many of them. We're looking at them right there. It's that purple shading in the middle, right? So I'm going to take that situation over on the right, and I'm going to mimic it over on the left and try to transfer that understanding, which I hope that's pretty simple, I think, to understand. Take that understanding and transfer it to the white problem up at the top. So here we go. So one of the problems is going to say, and I'll keep the colors consistent, that the stuff inside the absolute value, x plus 2, could be greater than or equal to the opposite of my boundary. What's the opposite? This is the boundary here. What is the opposite of my boundary? 1/2 of x plus 6. Well played. And then I'm going to write the word and. And then again, color coding, I'll switch to green. What does the green one look like over here? X plus 2 is wonderful. And that, again, if you're going to get this and use this method, which in the end really will save you time, FYI, you better understand that every little nuancy sign matters. Every little greater than, every little less than, every when do I change the sign, every when don't I change the sign. But that green and red, if that makes sense to you, then you're someone who might like this method. I don't know. Now let's solve the problems and watch what happens. So we've created them. That's the hard part. Now comes the easy part, just doing basic algebra. On both of these, I am going to go fraction killing. So I'm going to just multiply everything that I see by 2 on both sides. So what does my red one become? Mhm. Is greater than or equal to? Yeah, wonderful. How about the green one? What's he become? Is less than or equal to? Nice. Fractions are out of the way. Life is good. So let's solve the red guy. Let's press on. If you bring your x over to the left, you only get 1x. Keep your sign the same. Bring the 4 over. You get 8. And we've figured out one of our 2 constraints now. Okay. And then I'm going to copy down the big critical word and. Cannot stress again enough the importance of that word and. On the one on the right, the green one, if I bring my x across, I get 3 x's. I better show a little work on this one. And if I bring the 4 across, I get negative 16. And so I'm going to write this one. I'm electing to write this one just so that this will make more sense to everybody, that x is less than or equal to negative 5 and 1/3. I'm electing to write it as a mixed number just so that it's something we can hold on to a little bit tighter. And this is where you have to come to consensus, like you and your brain together. And let's think about what this looks like. If I were to graph this, and this graph, by the way, is not the kind of graph that you would ever leave on a quiz. I mean, it could be there, but you dang well better like cross it out or something, because the graph that we're about to make is defective, bunk, no bueno. But what it does is it serves a purpose for us to see why the answer to this problem is what it is. So we're going to put our boundaries in place, and now we're going to let ourselves see. If you've made any math errors prior to this, then this is all lost. That's what's so hard about this section, is that the smallest little mistake and you're done. Done. But if every little sign change, every little thing we've done has been perfect, then the red graph looks like this. And the green graph looks like this. What's the solution to this problem? There is no solution to this problem. And why is that? Correct. And the key here is the faithful transferring down of this critical word and. The and, unlike the last problem, tells us that both of these have to be true. In order to solve an and problem, both requirements have to be met. And like you said, there are no numbers in the known universe that are simultaneously less than 5 or negative 5 and also greater than positive 8. So this graph is it's fine for showing your work, but it's not the graph that we want to present. What is the graph of our answer going to look like? It's just going to be a buck naked number line. Remember that when we go to graph no solution, we just draw a number line and move on with our day. So as far as what's the solution, it's this in the red box. What's the graph? It's this in the red oval. So that is another method that you're welcome to start using. And what it does is it throws us right into the ending phase without having, I mean, we're still finding boundaries. We're just not going through and testing points and trying to make sense of it that way. So I would say that we could do more together, but quite honestly, I think it's best at this point if you just work, and then just let me know what I can do for you. Okay. So you pick, you can do it old way or try the new way today if you're feeling you like that. It's up to you. But I'll leave the recording going. I'll pause it as I always do. And if you have questions and want to go over another problem, I'll unpause. All right, cool. Yeah, so number 4's got some funk to it. I assume that you're using the other method, the old method. Did you try the new one today? Oh, get a kid. Yay! Hey-oh! Boy, that's music to my heart. That's super. Well, I'm so glad to hear you say it. Just proves that the way I did it for 20 years, I wasn't really harming kids at all. Or maybe you like this method better just because compared to the other one, I don't know. But either way, this is rad. Okay, so I'm going to do it the new way. So we have the absolute, am I recording? Oh yeah, I am. I talk way too much. So we have the absolute value of 2x minus 8 is less than, so we know this is going to be an and situation, negative 3x minus 4. So when we think and, we're thinking sandwich. We're thinking I want to be bigger than the small boundary and less than the high boundary. So my left side is going to say that 2x minus 8 needs to be greater than or equal to the opposite boundary, which is 3x plus 4. My other side of it is going to say that 2x minus 8 has to be less than or equal to the regular or positive boundary, which is negative 3x minus 4. So did you get this far? Oh yeah. I didn't want, but I mean, was this a success, this step? Wonderful news. So the one on the left, when I solved it, I just kept it simple. I just kept my x on the left. So I subtracted 3x, I added 8, and then I divided by negative 1. And this one switches to x is less than or equal to negative 12. So far, so good. Wonderful. You're on a roll. And then I'm going to copy the critical word and then for my green one, if I add 3x, I get 5x. And then if I add 8, I get 4. And then I'm going to say that x is less than or equal to 4/5. This is, to me, one of the harder ones. But again, this is where I think the new method really shines because we're going to have a nice, I think, good, solid visual look at the situation. But the key is a graph. Like to me, even if the graph that I'm about to make, like you'll see if you ever look at my answer key, that the graph that I made first isn't the graph of my answer. It was the graph that I used to help me make sense of the answer. So I'm going to put negative 12 over here. And of course, I'm going to put 4/5 over here. And again, it's this word that is going to carry the day. So to be less than or equal to negative 12 is like this. Yeah. To be less than or equal to 4/5 is like this. The key here is that if it said or, then everything in the green and the red would work. So like if I said to you, you can be less than 4/5 or you can be less than negative 12, then you could pick anything. Like you could pick 0 because that's like less than one of them, right? But the key when it says and is again that they both have to be true. Correct. And so when it says and you've got two inequalities that are flowing in the same direction, to make them both happy, you have to pick the one that's further along. So the overall answer to this problem is not what you see written up here. This is just a step along the way. The overall answer to this problem is that x has to be less than or equal to negative 12. That's what we box up and present as an answer. And again, that graph that you see on the board is not an answer graph. That was my work. That was my brain trying to figure out what to do. So the answer is actually, the answer is a nice little old school, simple algebra 1 looking situation where all I need is negative 12, right? With a closed circle, shading to the left, and I'm done. So the answers to this problem are the things in the white boxes. Anything else on the board was just the work to get there. That feel good? That's awesome. Yeah, yeah, which one? No problem. Yeah, no problem at all. So I'll pause again. If you guys want to go over more stuff, just let me know. So let's say we were doing an old problem, something like the absolute value of 2x minus 4 is less than like 10. So you could use it for that too. You could say that 2x minus 4 is greater than negative 10, and 2x minus 4 is less than positive 10. And this way here, again, if you do it the new way, even with the old school number ones without variables, you can still find your solution set this way. Like you could theoretically never do one the testing regions way again. Just FYI, if you know what you're doing. So 100%. Totally.